You ever click on a tiny link, like a bit.ly or something, and just not think about it? Of course you have. We all do. But what's actually happening behind the scenes is honestly kind of amazing. It's this super high performance system that has to handle billions of requests. So today, we're going to pull back the curtain on the surprisingly deep engineering of URL shorteners. You've definitely seen one of these before. It's just a monster of a URL. It's got all these tracking codes and session IDs. It's just a mess. You can't share it, you'd never remember it. It's basically digital spaghetti. So if you're an engineer, this is the big question, right? How in the world do you take that complete monstrosity and turn it into something clean and simple?
Something like this. A link that's actually clean, compact and super easy to share. We use these things every single day and just take them for granted.
And yeah, it feels like it's just magic. But it's not. It's actually a total masterclass in system design. This delicate balancing act between massive scale, incredible speed, and airtight security. Okay, let's really get into it. All right, so first things first, the absolute heart of the problem is this. How do you even create a unique shortcode for any long URL the world throws at you? At its core, URL shortening is really just a mapping problem. You're taking this almost infinite universe of long, messy URLs and trying to give each one a unique, tiny little key in a much, much smaller address book. So your first idea might be to just use a hash function, something like MD5, right? You take the long URL, you generate this unique digital fingerprint, you chop it down to a manageable size, and then you encode it into a short string. Seems simple enough. And it's deterministic, which means the same long URL will always spit out the same short one. What could go wrong? Well, here's the catch. That chopping it down part is the problem. What happens when two totally different long URLs just happen to produce the exact same shortcode after you've truncated them? That's what we call a hash collision. And this is where that simple idea just completely falls apart at scale. To avoid sending someone to the wrong link, you have to check your database every single time you create a new short URL. You have to ask, hey, is this code already taken? And if it is, you got to add some random stuff to the original URL, hash it again, and just hope for the best. This check, then insert dance creates a huge, huge performance bottleneck. Okay, so if that's not going to work for billions of links, how do you do it? How do you guarantee every single code is unique without grinding the whole system to a halt? Well, the real solution, the one the pros use, is to flip the entire problem on its head. Instead of creating a code and then checking if it's unique, you generate a globally unique number first. Because if the number is one of a kind, you know the code you make from it will be too. No more checking, no more collision. Now, there are a couple of ways to do this. You could use a global counter, which is like a single ticket dispenser at a deli. It's simple, it's unique, but now everyone has to wait in line for a number. It's a new bottleneck. A much better way is range-based allocation. Here, a central coordinator, like Zookeeper, hands out big blocks of numbers to each of your servers. So one server gets IDs 1 to 1,000,000, another gets the next million, and so on. This is way better, but you still have that central service, which could be a point of failure. The real magic, the truly scalable solution, is a distributed ID generator, famously pioneered by Twitter with their Snowflake algorithm. Each server generates its own 64-bit unique IDs entirely in memory. It's so clever. It just combines three things: a super precise timestamp, a unique ID for the machine itself, the worker ID, and a little sequence number in case it creates multiple IDs in the same millisecond. The genius here is that every machine can do this on its own. No coordination, no bottleneck. This is how you generate millions of unique IDs per second. It's just brilliant. So awesome. We've figured out how to create links at an incredible scale. But what about the other side of the equation? What happens when people actually click on those links, which it turns out happens way, way more often? So get this. This is probably the single most important number that defines how these systems are built. The read-to-write ratio is often 100 to 1, sometimes even higher. For every one time a link is created, it gets clicked hundreds of times. That means your system has to be just ridiculously, overwhelmingly optimized for one thing: lightning-fast reads. And to get that speed, you build what's called a waterfall of caches. When you click a link, the request first checks the fastest place possible, your own browser's cache. If it's not there, it checks a nearby edge server on a CDN. Still no luck? Okay, it checks a super fast in-memory cache, like Redis. Only if all of those miss does it finally go all the way to the main database. And some systems are even smarter. They put a bloom filter right at the front, which acts like a bouncer at a club. It can instantly tell you if a link is definitely not on the list, saving you from wasting time looking for it. Now, a really important decision in all this is what kind of redirect to use. A 301 permanent redirect tells the browser to just remember the destination forever. That's super fast for the user, but it means you get zero analytics after that first click. A 302 temporary redirect, on the other hand, tells the browser to check back with your server every single time. This lets you track clicks accurately and even change where the link points later on. That's why most services use the 302. But of course, anytime you have a simple, powerful tool on the internet, you're going to have people trying to abuse it. So any system that's going to survive in the real world needs some serious defenses against people trying to hide nasty, malicious links. And that means layers of security. When a new URL comes in, it gets checked against services like Google Safe Browsing. To stop hackers from just guessing links by counting up, the IDs are made non-sequential. They use clever tricks to shuffle the bits around. Then you've got rate limiting to stop brute force attacks. And finally, you absolutely have to encrypt the original long URLs in your database, so if you ever get breached, user data is protected. Okay, so we've got our unique 64-bit number. We're almost there. But that's just a long number, not the nice, short, readable string we see in the link. So what's the final step? The final step is base encoding. Now, you've got options. Base 64 is really compact, but it uses characters like the plus sign that can break URLs. Base 58 is cool because it removes letters and numbers that look alike, like a 0 and a capital O. So it's easy for humans to read. But the industry standard, the Goldilocks choice, is base 62. It's just letters and numbers, nothing else. It's the perfect balance of being really compact while also being completely safe to use in a URL. And just how powerful is base 62? Well, get this. With only 7 characters, you can represent about 3.5 trillion unique links. That is more than enough capacity for pretty much any service on the planet for a very, very long time. So there you have it. We went from a simple hashing idea that just doesn't scale to the coordination-free brilliance of a distributed ID generator. We saw how you have to optimize everything for that 100-to-1 read ratio with a waterfall of caches. And then we layered on all the security to keep it safe. The humble URL shortener is, really, a masterclass in modern system design. But it kind of leaves you with one last big question. These little tools have become a kind of invisible, critical infrastructure for the internet. They're quietly directing huge amounts of traffic, controlling the very paths of information online. And as they become more and more essential, it makes you wonder, who should we really be trusting to draw that map?